Hello, can you hear me?
Yep, can you hear me?
Yes, good.
Okay, great.
Shall we start?
Yes, sure.
All
Sure,
right.
sure.
I can hear you typing.
Sorry, I will turn off my my microphone.
That's all
I'm
right. That's
alone.
all right. That's all right.
There is only one student arriving now, so I was a bit absent. Sorry.
That's okay. I was just wondering. All right. So today, for the rest of the lectures, the next 3 or 2.5, I think, I'll be talking about active region magnetic fields, more concentrated on the stronger fields in active regions and the relationship to flares and CMEs, for example. It will also be a sort of introductory on various research topics. So it won't be complete, and it will certainly have some personal bias. But I hope to get you a sense of the basics as well as the frontiers in the field. All right, so first we'll go over the flux emergence, the basics of flux emergence we didn't get to talk about last week. And then I'll talk about flares and CME basics with focus on the magnetic field as usual. Okay, so the reference here is this Cho and ISO 2014 living review in solar physics. It's a pretty complete review, and I have to admit this is not my expertise. So if I say anything wrong, please correct me. Matthias in his first part of the lecture talked extensively about the theory of dynamo. Okay, so when it is actually in action, what we can observe, mostly in photosphere, are maps like this. Okay, so here are 3 examples. On the first row, on the left, I think it's the Hinode SP data of the quiet sun. You can see these salt and pepper colors of the longitudinal field, which basically outlines the edge of the supergranules, for example, and they will usually have a few flux density. Okay, in this case, at this particular resolution of several tens of Gauss to 100 Gauss at most, but the intrinsic field strength, there's still some debate to it, but people think it might be even stronger. It only has a smaller filling factor. Okay, but if you watch the movie, sequence of these observations, these magnetic fields are being carried. At least appears to be by the convection, and they actually have a turnover time of minutes to hours. So you're constantly being supplied by a sea of these salt and pepper. Okay, whereas if you think about active regions, they emerge, they live for a much longer time, on the order of days or weeks. Okay. So these are different spatial and temporal scales. The smaller scale magnetic fields live shorter, and the stronger and larger patches live longer. So what you can do is to make statistics, from these observations. So the left is Hinode I just mentioned, and the middle, I believe it's MDI high resolution. That MDI is an instrument on SOHO. It's the like the father of HMI. It has a lower resolution. It's full disk, but has a lower resolution. This is a higher resolution mode of the instrument, which observes a smaller field of view and has a resolution, I think, about 2 arcseconds. And on the right-hand side is the full disk MDI that has a resolution of 4 arcseconds. Okay. So what you can do is you segment these longitudinal field into different patches and mark them, okay, and track them over a course, for hours and days, and see how long they live and how fast they appear and reappear, and you count them, okay. So what you find is that these, smaller scale fields gets a turnover much faster, and comes up in much greater amount than active region. And we've already, understood that the active regions, they come and go with a very strong cycle dependence. But, if you do this for the statistics for the quiet sun, you will see that it might also have some trends, with respect to the cycle, but the trend seems to be weaker. So if you think about, the way they are generated, people have been talking about there might be two different dynamos. One is operating on a global scale that generates these cycle-dependent active regions, okay, with a very specific geometric laws like Joule's law and Joyce's law and Hill's law. And then you have these, smaller scales that basically do not care so much about cycles. Okay, so the thought is that there might be two different dynamo process in operation at the same time. One is operating in a deeper convection zone. One is perhaps operating in a near surface layer. But okay, so if you actually look at the numbers, so on the left-hand side is statistics of magnetic flux in each of these individual patches. Okay, and the vertical axis is their appearance frequency. Okay, how often they actually emerge. So people have been doing this since the early 1990s, like in Karen Harvey's dissertation, where she looked at the sunspots exclusively, because at that time we don't have a very high resolution, observation of the quiet sun. But later on, in 2000s, when we have MDI and Daniel-Nodi, we start to, probe in a similar fashion, smaller and smaller scale fluxes. And all of these statistics follow a very, continuous power law. Okay, so the smaller scale the flux patch is, the more numerous they are, and it has a power law in a slope of about 1.8. And if you actually integrate the flux, okay, unsigned flux, of course, if you integrate the signed flux, it's basically zero. It should balance. But if you integrate the unsigned flux, you will find that because of the slope, is relatively steep, you have a weaker tail where the active region lives on the lower right, right? Then you have a stronger contribution of the quiescent flux on the left-hand side. And the amount of quiescent flux, the unsigned flux, is actually much, much greater than active region flux, like 10,000 times, okay? And because of this continuous power law distribution, usually, as you probably have seen many times, whenever you do the statistics and you find a very consistent power law, usually it says something about the underlying physics. It's probably operating with the same kind of physics. So at least in the review paper, the authors propose that perhaps it is a continuous dynamo process operating in the convection zone. It just has they just have a very different, scales. And we know that the dynamo process is strongly affected by the Rossby number, which is basically a measure of how important the stellar rotation compared to your convection time. Convection. Okay, so if you have a fast rotation, which means that your Coriolis force is stronger, your dynamo process will be more strongly modulated by these global processes like the cycles and so on. But when you consider smaller scales, okay, then the stellar rotation for sun is about a month. That is much longer than the smaller scale convection turnover time, okay, for granules and supergranules. So in that case, in the smaller dynamo case, okay, then the global processes is no longer that important. So that's why we see a cycle dependence for the larger scale active region magnetic field, whereas we don't see such a strong dependence on cycle for the smaller scales. All right. So the idea is that we have one continuous dynamo process. It's just has a different dependence on the stellar rotation depending on their relative Rossby number. All right. So since we're talking about active region, it's worthwhile to look at what the flux emergence rate in detail for active region. So here is a diagram showing you on the x-axis is the flux in each active region, okay? And the vertical axis is the flux emergence rate, okay? So how much flux is emerged within 1 hour. So this is a diagram compiled by Norton et al. And there are legends here. So basically what it says is that the blue curves, okay, the blue symbols, okay, they are from observations. So we have these, on the lower left, two, axes there are smaller active regions or ephemeral regions. On the upper right, we see these squares with error bars. That's a sample of active regions from Torrielmi, for example. All right. And you can do the same for models, okay, numerical models of flux emergence. I don't know if these models are fully self-consistent. For example, if you specify the flux emergence rate is completely, consistent with, and you don't have to specify anything. Okay, I don't know if that's the case. But what it appears to be is that both the observation and the simulations follow this similar power law. Okay, so the fast the larger the active region is, the faster the flux emergence rate is. Okay, so the effect is that it always takes about maybe a day or several days, for the flux to emerge from in a whole active region. The time scale is like half a day or a few days. Okay, it's not going to be a few weeks. It's not going to be only like 1 hour or two. Okay, it's always going to be on that day-ish time scale. So this is sort of empirical, or observational constraint. Well, why that is the case, it is not clear, at least. So, what is the physics of the flux emergence? Okay, so if you think about flux emergence as a flux tube, all right, bundle flux in the active region, right? So the pressure needs to be balanced inside and outside the flux tube, all right? So inside the flux tube, we have the regular gas pressure, Pi. Then we also have the magnetic field magnetic pressure, which scales as B squared. So this needs to be the same, okay, comparable to the external magnetic field free convection zone plasma. So if that's the case, all right, then the internal pressure will be, gas pressure will be less than the external gas pressure, all right? The consequence is that your density, if your temperature is the same, okay, then your density will be, inside the flux tube will be smaller than the external density, okay? Then you will experience a buoyancy force, okay? So the flux tube will start to rise, okay? So that's natural. That's a consequence of having a magnetic field. Or this doesn't specify where the magnetic field comes from. We just assume it's there for now, okay? We need to characterize, how this flux tube evolve or arise in the convection zone. Okay, one way to do that is we take a look at how the different variables scales with radius. Okay, here I'm writing as z. Basically, it's just height or the radius you can think of. So the pressure as you move from the deeper convection zone to the surface decreases. All right. And one way to characterize the decrease of pressure is to look at the pressure scale height, which is the distance for the pressure to decrease by a factor of E. Okay, and near the top of convection zone, that height is very small. It's about 150 kilometers. Okay, but deeper in the convection zone, it's much bigger. So what happens is that once you're circular, assuming it's originally the flux tube is circular, then it starts to rise, okay? It will, if it maintains it, suppose it's maintaining its shape, okay? Then the same flux tube diameter will span more and more scale height, right? So there will be larger and larger pressure differences between the top and the bottom of your flux tube, okay? And the bottom will have a larger pressure, right? So if it's, still circular, then you will have a larger pressure on the bottom and smaller pressure on the top. So the net effect is that the larger pressure will just press on the magnetic flux tube, and then it will squish it, okay? So it becomes flatter and flatter as it rises through the convection zone. So, and this is what the cartoon down there shows, as predicted by Spread. So that's actually a very reliable or robust feature of flux emergence in simulation. Of course, in observations, we are still not able to tell the difference even through helioseismology just yet. Okay. And the other point is that because the convection energy is larger, generally larger, the plasma beta is bigger than 1. Of course, it's plasma dominating convection zone. So you will need, if you compare the magnetic field energy and the convection energy, you will need to have a very strong field, okay, to have the similar amount of energy or comparable energy to the convection kinetic energy. And this is the so-called equipartition energy. And the magnetic field required to reach that equipartition energy is on the order of 10 kilogauss in deep convection zone. So basically, in order for your flux tube to stay more or less coherent, you will need that very strong field, on the bottom of at the bottom of convection zone. So you will need some mechanism to generate that strong field, down there. All right. So we talked about these flux tubes are getting squished as it emerge. Okay. But I mean, it is possible that in some conditions, these kind of perturbers will be stable. Okay, so there might be some restoring force to stop the flux tube from emerging. Or it's also possible, if the condition is met, that this disturbance will be unstable. The stratification will be unstable. So once it starts to rise, it will start rising, and you can't stop it. Okay. So the way to tell one from the other is to look at the stratification, the actual, change rate of density with respect to height. And this density variation will be different inside the flux tube and outside the flux tube. Okay, so outside flux tube is just the ambient, quasi-steady stellar interior. Okay, so you have a profile. But internal to the flux tube, because the flux tube is rising, the heat, exchange time scale is smaller compared to your rise time. So we generally assume that the process is adiabatic. So there's no heat exchange, okay, between the flux tube inside and outside. And also, because the heat does not exchange inside and outside, your specific entropy does not change, right? So if you work out the force balance, so if your adiabatic density stratification is smaller than your the ambient density stratification, the perturbation will be unstable. Or if you rewrite it, okay, it's basically the change of temperature with respect to the pressure, okay, in adiabatic situation or in the ambient stellar convection zone. So if that is met, okay, the stratification is called the super adiabatic, okay. And if that's not met, then it's subadiabatic. So when it's super adiabatic, the flux tube disturbance will be unstable. So on the right-hand side is a diagram of the this super adiabatic or subadiabatic conditions at the near surface layer and photosphere. Okay, so this is 0. That's the surface, and this which line? This dotted line, I think, dotted line is the ambient stratification. Okay, it's like this. Okay, and this this solid line is the adiabatic stratification. Okay, and if you subtract the two, this dashed line is their difference. So when this delta, the difference is smaller than 0, it's super adiabatic, which means the disturbance is unstable. The stratification is unstable. Oh no, sorry. I think it's the, maybe I plotted it wrong. Okay, so, oh no, it's correct. So when it's bigger than 0, yeah, when this difference is bigger than 0, it's super adiabatic. Okay, so you can see that below 0, below the surface, everything is super adiabatic. So the flex tube, once the flex tube gets disturbed and starts to rise, it will not stop. Okay. So that is, why basically flux emergence is a natural consequence of the internal stratification of the sun. All right. But the interesting thing here is that once you get through the surface, it becomes sub-adiabatic. That means that, once the flux tube reaches the surface, it is stable, okay? You need some other mechanism to make it break through the surface. So it is natural for the flux tube to rise in the convection zone, but it is not natural at all for the flux tube to actually break through and emerge into the corona. So that is an interesting thing that, an interesting concept that you should have in mind. The other thing is that because of the during the emergence process, these flux tubes will be susceptible to various instabilities. Okay, there is a detailed description of various types in that review paper. I would refer you to. So one consequence is that once the flux reaches near the surface, all right, then it becomes squashed. Okay, when that happens, okay, your field strength would actually becomes weaker because it's spread it out. All right, so if the field strength becomes so weak, it is no longer comparable to the kinetic energy. It might be shredded. Okay, so assume that horizontal expansion will not stop, then the flux tube will no longer stay coherent. And that is not what we observe because we need the flux tube to be coherent to emerge. So we need to, there should be some mechanism to stop the flux tube from, expanding horizontally indefinitely. Okay. So one mechanism is that if your flux tube is twisted somehow, okay, it will stay more coherent than an untwisted flux tube. All right. So this is what on the lower, page show you a simulation in the stellar convection zone. So this is a star that's rotating faster than the sun, and you have these toroidal flux tubes generated, and it will undergo these, instabilities, and you see these kinks, and part of it will rise through the surface. All right. Okay, so we talk about the twist. Okay, so this is what we actually observe in active regions. So it seems to be inherent. Most of the active region will have some, twist, some amount of twist. All right. And we talked about this dependence of the dynamo, and it's on the Rossby number. Okay, for the larger scales, because the convection time scales is larger, so we have a small Rossby number, and the larger scale structure will be more susceptible to Coriolis force. So it should have a more coherent pattern. Okay, either in time, like dependent on cycle, or in space, like you have a more coherent law of Hale's law or Joyce's law. All right. Dina Lonko and collaborators in 1990s proposed this so-called sigma. This is sigma, right? This is sigma. Okay, sigma effect. That explain the origin of the twist and right. So by twist, I mean, so if you have a straight flux tube, the rotation of your magnetic field lines with respect to the axis of your flux tube. Okay, so that's the twist. And then you have writhe, which means the bodily kink of the whole flux tube. So if you look at this lower left plot, the twist is how the blue field line moves with respect to the central red field line. And the writhe is the whole flux tube has this kind of omega shape. Okay. So the idea is that the helicity, we briefly mentioned it, Matthias also talked about it, and you will see that in homework. The helicity is a measure of how twist or how much writhe a flux tube contains. Okay, and it is a conserved value in ideal MHD, so it should not change. So for isolated flux tube, it should not change. And if under simplification, this total helicity will be the sum of a measure of twist and a measure of writhe. Okay, it doesn't matter how we define those, but it should consist of these two terms. Okay, and it also scales as the flux inside the flux tube squared. So this sigma effect states that we can generate twist inside the flux tube even if the flux tube originally doesn't have any twist. We only need to have an opposite sign of writhe. Okay, so if initially we have an untwisted flux tube, as soon as we some kind of mechanism, for example, in these papers, it's specified as an interaction between the flux tube and turbulence and kinetic helicity, okay, how the fluid move with the helicity. So if it interacts with convection and develops some kind of kink or writhe, so it has a particular sign, either left-handed or right-handed, okay. So by the requirement of helicity conservation, your twist will go the other way, okay. So if that is satisfied, so we have a kinked flux tube with a twist, then the flux tube is more likely to survive the flux emergence, all right? And here's an example of flux emergence, and you have some kink, you have some writhe, and at the surface, this is what you see in the surface magnetogram, okay? You have positive and negative, and near the neutral line, okay, the so-called shear, which means that the vector, or horizontal vector, is no longer perpendicular to the neutral line. Okay, if it's there's no shear or the field is potential, these horizontal field vectors should be perpendicular to the neutral line. If you have shear, it's more parallel. Okay, or you have some kind of twist. That will be obvious if you look at the motion of active region. Sometimes it just rotates. If you remember from last week's movie, or if you look at the field vector, sometimes you can see a coherent rotation of the field vectors in the photosphere. Or if you look at EUV or X-ray movies of single sunspots, very often you will see that cartwheel type of loops. Okay, so that also tells you there's some twist. All right, and that is actually the source of solar eruptions, as we'll discuss later. So how do we test this sigma effect? Okay, so this is a very interesting, but it might be somewhat abstract test using the statistics of sunspots. Okay, so what this author did was to gather simple bipolar sunspots of all the sunspots, all the active regions HMI observed. And you measure the twist and writhe, these two quantities in these bipolar active regions, and look at their signs. Okay, so if their signs are the same, okay, so it is less likely that the initial flux tube does not have a twist. Does that make sense? So if the initial flux tube does not have any twist, in order to generate twist, it has to convert part of the twist to writhe, and these two will have different signs. Okay, so if the initial flux tube does not have any twist, what we should see is twist plus writhe, the sign of these two. If they multiply the sign of these two, will be less than 0. Okay, for those plus than 0, for if you the sign of these two quantities are the same, okay, it is likely that the initial flux tube does not have twist, or you can say that it's more likely that the initial flux tube has some twist, and that twist should come from some kind of dynamo, action. Okay, so if we separate these two classes, on the top is the twist multiplied by writhe bigger than 0, which means the initial flux tube has some twist, and you look at north and south hemisphere and look at their signs. Okay, the sign of their twist are sort of half and half. It's about 64. Okay, the preference is about 64. So there's a weak hemispheric dependency. Okay, Whenever there's a strong hemispheric dependency, okay, that we think, as we said, this dynamo, large-scale dynamo, is modulated by the rotation, right? But then here we have a very relatively weak dependence of the hemisphere. So it seems that the initial twist generated by dynamo does not have a very strong hemisphere dependence. Okay. Now, if we look at this, okay, look at the twist and right have different signs, which means that the flux tube initially does not have much twist. Then it actually has a quite interesting, very stronger, much stronger, hemisphere dependence. This is the effect of this is the sigma effect we just talked about. So it appears to be, okay, at least from the small sample statistics, that the sigma effect might play a larger role in determining the sign of twist of these active regions. Okay, so this is sort of an empirical statistics study that gives some weight to this sigma effect. All right. We talked about the process in the convection zone. Then we talked about this super adiabatic and the subadiabatic. Okay, remember that below the surface it's super adiabatic, so a rise of flux tube is natural. But when it gets to the surface, what happens is that the flux basically stalls. It hits a wall. It just stays there. Okay. Then you have more flux coming from below. It just piles up near the surface. Okay. Then, okay, what happens is that your magnetic field gets strengthened and your field gets stronger. Okay. And some of the field will actually eventually be brought up by convections, like what this cartoon shows. Okay. So what you get is these kind of serpentine field lines. And if you look at the magnetogram, so you will see positive, negative, okay, moving apart from each other. And then you will see other positive and negative moving from each other. Okay, then they are connected by these undulating or serpentine field lines. In the magnetogram, you will see these salt and pepper, basically, patches moving away from each other. It's very fragmented, okay? So one mechanism to actually make the whole flux tube emerge is by reconnection. Okay, so we know that there's convection like this. It brings part of the flux tube up, and then it makes these two positive and negative converge, and they will eventually collide. Okay, and reconnect. So what happens is that you will generate these kind of O loops. Okay, and get rid some of the mass that is actually above the field line. Okay. So once you get these heavier mass from the tube and above the tube, then this flux tube becomes more coherent and actually emerged. Okay, so the idea is that by interacting with the surface convections and turbulence, you will first fragment your flux tube, then they coalesce. Okay, so the idea is not for the flux tube to emerge as a whole, but fragment it, then reconnect, and then emerge. And this picture seems to be consistent with what we see in the observation. You have these very fragmented salt and pepper near the neutral line, and they're separating. Then they, sort of gather together of the same sign, and create stronger field concentrations like the sunspots. Okay. So another example of flux emergence. Okay, so let me play this one. So this is it's a simpler flux emergence active region. So see at the center, so these stars are just the centroid of the positive and negative that I calculate. Okay, so you have separation, and then the whole active region actually rotates clockwise a little bit. Okay, you can see that as a sign of rise. Okay. So this is a sort of bipolar, very clean bipolar emergence. Let me play that again. First, you have the separation, and it's very fragmented. Okay, then these flux patches sort of coalesce. Okay, and the whole thing starts to rotate a little bit. Okay, you can see that as the twist propagating from the internal convection zone to the surface. So this is a process over several days, I think. Okay, so time scale is about days. So this is the one we saw last time. Okay, it's a more complex flux emergence, but the basic idea is the same. The additional component is the interaction, at least what appears to be on the surface, between the central, this one, and this one. It is not clear whether, under the convection zone, the central bipoles are connected. Okay, there's it. So the obvious thing is that these two should be initially connected, and the top two should be initially connected because we see that they are separating away from each other. What we don't know is whether the central two bipoles are connected, or whether it was a serpentine type of connectivity at the beginning. Whether there's 1, 2, 1, 2, okay, it's not very clear, But so the question is, okay, so if you were to predict flare and CME, if you compare this one with the previous one, which one is more likely to produce flare? Any thoughts?
We vote for this one.
Okay, can any students explain why? Do you have a reasoning for that?
Because this one appears to have a more complex magnetic field geometry, whereas the other one had what looks like a very simple bipole magnetic field. So this one that has a more complex magnetic field has a much greater likelihood of field lines crossing and reconnecting, thus producing a flare.
Okay. Yes, that's exactly right. Well, any somebody's talking. Somebody else is talking? No? Okay. So that's exactly correct. This is more complex, okay? But you can also think about in terms of magnetic energy, okay? So we'll talk about it in a minute, and also in homework. The idea is that all the flares and CMEs are driven by magnetic energy, okay? But it is not all the magnetic field energy, okay? So it is not the whole coronal magnetic field is just gonna convert it to other energy right away and nothing will be left. Well, if that's the case, the sunspot will disappear, altogether, right? But that's not the case. So what happens is that by the constraint of helicity conservation, as well as your surface field, okay, so let me say that again. Because the surface of the high density and slower velocity, typical velocity, okay, so it should evolve slower than the corona. So which means that during the flare time, your surface field should not change as much as the corona field, okay? So if that's true, and also the helicity holds constant, there's a so-called the Wattier's law theorem that the potential energy, okay, the potential field corresponding to your surface boundary condition is the lowest energy state. So you can release only the part of magnetic energy above that lower energy limit. So there's only a small portion of energy could be magnetic energy could be released. And what happens is that in a complex active region like this, you have shear, you have rotation, you have polarity interaction, you have cancellation, you have emergence, whatever, okay. It is non-potential. You have electric currents, okay, the curl is not zero. So you will have a higher magnetic free energy. So you will have more energy available to release to power big flares. Whereas for a simple active region like this, you will have less free energy, most likely, okay? So from an energetic point of view, okay, that is the argument, okay? And I probably know that, people are using this magnetogram alone, even without models, to predict flares with some success. And the idea is also, it doesn't matter what you use, machine learning or whatever, the idea is to look for the energetic features, such as currents or twists or writhe, for example. All right, very good. So we talked about flux emergence, that's what we observe in the photosphere. Okay, so once your flux goes through that surface, once we see that black and white photospheric maps, there's already a lot of flux in chromosphere and corona already. We just saw that layer. Okay, so the consequence, is already apparent in the corona, even before you have so much flux, in the photosphere. So this is example of observation from SDO combining HMI on the right and AIA on the left. Okay, let me play this movie. So you have this white and some of the black emerging, but this white is sort of encircled by the negative flux. Okay. So if you imagine the connectivity of the coronal field lines, you would think of, part of the positive is connected to this negative flux, and part of it's connecting to this part of flux. So it will produce a dome-like structure. It's a closed dome structure, right? Just as what you see on the left-hand side. And this is a kind of a particularly interesting magnetic topology that I'll probably talk about in the next class. It's called the fan spine topology. And usually you would expect a magnetic null point on top of this dome. But what I want to emphasize is that once you start to emerge flux in the photosphere, okay, your coronal field connectivity will change. Okay, imagine if when there was this white flux at all, this black flux is probably connecting to somewhere else, further away, positive flux. Okay, or it might be open. But once it starts to emerge, the lower energy states, as the nature chooses to obtain, okay, is what we see here. It will connect down to the newly emerged flux, okay. And if you want to change the connectivity of the coronal loops, you will have to go through reconnection, okay, at least on such a short time scale. You will have to go through reconnection. And if you reconnect, you will release part of the energy, magnetic energy. Okay, so that energy will heat the corona, and as you see in this particular channel 211, it gets brighter and brighter. All right. So you can actually figure out ways to estimate how much energy is released, through topological analysis. For example, in this paper, so the authors did such analysis, and over several days, okay, because of this relatively quiescent flux emergence, you will get the total released magnetic energy of this order, 7 times 10 to the 30th erg. The one number you probably need to remember is that for an X-class flare, the energy is 10 to the 32, okay? So M-class flare is 10 to the 31. So this is comparable to M-class flare spread it out over several days, okay? So it's sort of a quiescent release of magnetic energy that is actually heating the corona. So I'm trying something new here. I'm trying to ask more questions, okay? Question, so do you think the active region flux emergence is important to coronal heating, and why? Compared to quasi?
No.
Yeah.
No, because so many fewer active regions are present in the sun. Even though they release more energy.
It's not exactly a number, but it's the flux. You're correct.
Okay.
For the flux, yeah.
Because they contribute highly to the overall, or the global magnetic structure.
Yeah.
So shouldn't they contribute to coronal heating as well?
Right. That's exactly right. So the idea is that we talked about in the previous statistics. Okay, here. Yes. So the quasi unsigned flux is 10 to the 10,000 times of the active region at any moment. Okay, the flux emergence rate. So you will have a lot more small salt and peppers there, and the magnetic energy, if you square that, will be a lot more than the active region. Okay. And also just from the emergent frequency, active region only emerge locally, okay, once in a while. It's not expected to hit the whole corona. So what is important is the slope here, okay, in any kind of that quantity versus frequency, okay. Whenever there is a steep power law like this with a smaller tail, then the smaller scale things are more important, right? Whenever it's a more flat, or in X-ray, you would say the spectrum is harder, you will have a flatter or larger tail contribution. So the higher energy or larger, phenomena will contribute more. So in this case, obviously, quiet sun is important. And of course, they are not very obvious. Okay, if you use lower resolution observations, they don't really appear in your magnetogram at all, or lower temporal cadence, right? But they are very important to coronal heating. And that is exactly the reason that we want to build instruments like Hinode or Sunrise, the balloon, telescope, or DKIST. We want to see smaller and smaller scale to get to the bottom of the elemental flux tube, so we can get a better handle of the coronal heating. All right, very good. Okay, so well, this is a personal choice. Okay, so this is a so-called emerging dimming. So we talked about, I think at one point we talked about the importance of having multiple wavelengths. For example, for EUV, multiple wavelength observations, because we want to know we want a more complete temperature diagnostics. Okay, so this is a perfect example of that. So let me explain this. Okay, so on the left-hand side, we see two instances separated by 5 to 6 hours. Okay, it's a active region flux emergence. So you have this small dipole here. Okay, so you have a bigger dipole. Then if you look at AIA 171 channel, which is the cooler channel, has a temperature of 0.6 millikelvin. Originally, okay, so before flux emergence, or maybe you can see that, because there's some flux, you see a tiny loop here, all right? You see my cursor, where my cursor is, okay? But nothing much, okay? So if I don't tell you this is a new active region, you might think this is probably similar to, any flux patches nearby, all right? But okay, after several hours, okay, what you see is that, I don't know if you see clearly, okay, there is a dark C-shaped emission decrease, okay, in 171, okay. So if you outline the contour of the dimming, okay, on the magnetogram, it looks like this, okay. So okay, the intuition when you see something dims in a image, you might think it's getting cooler, okay. But that is not the case in this situation, okay. So you will need to think about what the EUV observations really means. What it really means is the amount of plasma in this particular temperature bin that my EUV filter is sensitive to. Okay, so when you have a dimming, which it only means that the particular amount of plasma in this particular temperature has decreased. It may be that the whole plasma is removed. It may also mean that the plasma is changing its temperature. Okay. So if you look at, so for AIA, we are lucky because we have multiple channels, right? We have temperature responses at different levels. So this is the dimming we see in 171, but when we go to higher temperature, 211, which is about 1 to 2 million Kelvin, we see a brightening, okay? So most likely, without performing any quantitative analysis, we are able to say, we probably will guess that it's plasma being heated actually, instead of cool off. Okay, so this is consistent of energy being pumped into the corona through flux emergence. Once it starts to emerge, you reconnect with the ambient flux, you heat the plasma. But with only one channel of observations, we will get actually decreasing emission. Okay, so this is the origin of emerging dimming. I think it's a very nice example of showing that in today's, with all kinds of satellites, we really should gather as much evidence from different channels as possible to get a better picture of the whole thing. All right. Oh, okay. I see one question from, actually, this is the end of this one, and I see one question here from chat. But there's a lot of quite some big field close to small scale heights and does not really reach the corona. That's a good question. You do not necessarily, okay. That's a question of how the energy is actually transported, how the energy is dissipated. And I don't have a good answer for that. The coronal heating mechanism now is the alpha waves and the nanoflare, okay? So the nanoflare scenario, these small flux tubes will reconnect with each other because of the inherent twist, okay? And it's so numerous that will heat the corona. And in the alpha wave scenario, the alpha wave will dissipate somehow in the corona, okay? I don't know their relation with respect to the field strength. So yeah, this is a question, that we're looking into, but I don't know the answer. Any more questions? All right. Okay, so if no questions, let's move on to these more drastic events. Okay, that's my favorite actually. So the reviews that I recommend are this Shibata-san, Maekara-san's review in Living Review of Solar Physics in 2011, and this Shriver review for the origin of large flares in CMEs. All right, so this has to be one of my favorite AIA movies. Okay, so I think it's 304, 193, and 335. So blue color is hotter, red color is cooler. Okay, so obviously something's going on the lower right. Okay, let me play this movie. So this is one of the rare cases that you have a very dense filament material being ejected, and partially, falls back to the sun. Okay. So there are so many things that you can study with this this kind of observations. Okay. So first, okay, the fall back of these cool materials when they hit the solar surface. That's where my cursor is. It brightens. You see brightening. Okay, presumably some kind of heating. Okay, so that could be understood or used as some kind of template for stellar accretion. Right? You have materials falling back to the stellar surface. Then, okay, you see, okay, when it starts, okay, you see a shock. You see the bubble. You see the bubble going out. That's a shock. Okay, you can estimate a lot of, properties of CMEs. And with this shock at the solar surface, you see these waves. It's not obvious in this movie, but if you do a difference movie, almost all large flares will have a global scale consequence of waves rippling through the whole sun. Okay. Yeah, and initially you also see these filaments right here. It has a sort of S-shaped. Okay, and that's a signature of twist there, so-called sigmoids. We'll talk about later on. So there are so many things going on. Of course, there's a CME going out you don't see. Okay, you will see this in coronagraphs. And there's the brightening of the pulse flare loops. Okay, so how do we actually reconcile all of these? Okay, so when we say flares and when we say CMEs, it sounds like they are two different mechanisms, two different phenomena. Okay, so the modern view is that they are actually a same process. Okay, you can have one without the other, but most of the time they occur in the same process. Okay, so I would highly recommend a reading of the so-called the solar flare myth paper by Jack Gosling in 1993. So for the solar flare observations went way back, because we have H-alpha observations and then X-ray. Okay, so the brightness, okay, left over by this eruption, whole eruption process will linger on for hours. You have H-alpha ribbons. Okay, in X-ray you have these post-flare loops, so they will be there for quite a while. So you see the brightening, the emission. That's the solar flare. However, the CME, coronal mass ejection, or in the early days called coronal transients, they are fast, okay? And we didn't have coronagraph until very relatively late. So we didn't really we didn't really know much about CME until later on, okay? So that was not the focus of the solar eruption studies. So we always thought that solar flare is the central thing. Okay, that's a fundamental thing that affects the Sun-Earth system. But in this paper, in 1993, even we don't have a very comprehensive observations. Gosling gave this diagram. I think that is pretty complete about the cause and effect in solar terrestrial physics. And he proposed that the CME is the central part and is, when you consider the interaction with Earth magnetosphere, for example, and the flare in CME is actually a coherent structure, okay? And this is further, proved with observations from SOHO, where we have a better view of CMEs. So this is one of the early observations with SOHO coronagraphs. Okay, so the x-axis is the time. Okay, the y-axis, the solid curve is the X-ray flux. Okay, so this is a very typical major flare profile. You have a sort of pre-flare rise where you have these X-ray brightening, small brightenings. Okay. Then it sort of increases gradually. Then you, for a few minutes, okay. Then you have a very fast rise, because that's called the rise phase. And then you have a decay phase. Okay, that goes on for hours and hours. It's a very typical long duration flare. With SOHO, we have coronagraphs. In particular, we have this so-called C1 coronagraph that images the very low corona. Well, unfortunately, it only operated for a couple of years, then it was broken. Okay, so we didn't get much observations out of that. But with the observations we had, these authors looked at the genesis of several CMEs. You can see the material moving, just as we just saw in the AI movies. Okay, we can track the filaments movements at different times, its heights. And if we take a time derivative of its location, we get velocity, and we take another derivative as the acceleration, and so on, all right? And we can say that it's basically very well synchronized with the emission, okay? We have initial phase, we have impulsive acceleration, then we have a sort of decrease in the acceleration. Okay, this is acceleration. Oh, this is velocity, sorry, excuse me. So the velocity will settle down to a sort of a constant level. Okay, so when the CME appears in C2, at about 2.5, 3 solar radii in the current coronagraph, it basically is moving in constant speed or decreasing a little bit. So the acceleration occurs in very low corona and has a time scale of tens of minutes at most. Okay, so these two phenomena, the emission and the kinetics of CMEs, are very well synchronized. There are also other lines of evidences that I'm not able to talk about here, but everything pointing to the same conclusion, that is the CME and flares as a whole process. Okay, so what is this process? Okay, the space weather has consequences, of course, so I'm just going to skip that. Okay, so what is this process? Okay, so we know that it's a process inherently magnetic phenomena. It's a process of energy release from magnetic field. Okay, we talked about the non-potential field. That part of magnetic field converted to some other kind of energy, including in flares, the emission, okay? You have flare ribbons, you have post-flare loops in UV and X-ray. These are the EM emissions, emission or radiative energy. Then you have the CME, kinetic energy, right? Then you have the high, high energy particle kinetic energy, for example, so on and so forth. And you have shocks. All these, will take part of the energy from the magnetic field, all right? So if we want to estimate the energy available, this is what we do, for order of magnitude or in the stellar parameter situation where we don't resolve it. We just look at the energy density, B squared, and then the scale of the active region, for example, L to the Q, okay? So if we rewrite it as a typical unit for active region, we have a kilograms field. For active region, it's about 30 megameters, okay? So the energy comes out to 10 to the 33 erg. So this is the total energy, okay? So remember, I said that for the large flares, X-class flares, is 10 to the 32. So what this means is that the free energy is usually on the order of 10% of the total energy, okay? And what's released in a flare is only a portion of the free energy. So it's only several percent usually of the total magnetic energy. So everything we talked, the flares and CMEs occurred in corona that has a time scale of minutes, okay, hours at most. But the thing is that the energy has to come from flux emergence, for example, right, and convection. And that has its own time scale of photosphere and convection zone. That is on the time scale of hours and days. So that's very different from the coronal time scale. So there's a very clear separation. What happens is that you will need to store this energy that's transported in parts. Okay, every hour you transported such a small amount of energy, and it cannot, dissipate rapidly. If that is the case, we won't have any energies. We won't have enough energy to power a flare. Okay, so we need this gradual energy injected from the photosphere to being stably held in the corona for a while. Okay, so a while means on the order of hours to days. Okay, so the storage is a problem. Okay, we need to address that. So the conclusion I'm just going to say here is the non-potential field. Okay, so when you have this twist and shear, the energy will be stored in that part of a stronger lower coronal field. You will have energy stored there in the form of, for example, electric currents. Okay. But then there's flare. Okay, then when the energy is so much that there's some kind of instability or reconnection is triggered. Okay, so that's another question of flare trigger. Okay, what triggers a flare? So that's a completely another set of questions. But if we don't think about that, we just think about what happened afterwards. The energy release will have an order of minutes, as I just said. So say that's 100 seconds. Okay. So we know that reconnection must be occurring, okay, and magnetic field must be diffused somehow. So we can estimate the diffusion time scale, okay. If we write that down, it's scaled as L squared over the magnetic diffusivity. If you just look at the induction equation, okay. If you take the magnetic diffusivity, the classical Spitzer value, okay, then you can write the diffusivity timescale as this. Okay, so this is the typical active region spatial scale. This is the typical active region temperature. Okay, it's dependent on scale and temperature, million Kelvin. So the time scale will be 10 to the 14 second, and that is impossible because we know that the corona, the diffusion happens on a time scale of 100 seconds. Okay. So the way out of this is either you have a extremely high temperature, which is unlikely because we don't observe it, or it's the other possibility is you make the diffusion region, okay, very, very, very localized. Okay, so in order to get the diffusion time scale down to 100 seconds, by virtue of this back of envelope estimate, you will have a diffusion time scale, spatial scale of about 10 meters. Okay. So the diffusion region in a reconnection is just this central current sheet layer. So the width of the current sheet layer, if we assume this classical diffusivity will be on the order of 10 meters, and it's under the resolution of all instruments right now. But assume that's what is happening. Okay, so we will need current sheet in the corona. Okay, that magnetic field starts to reconnect and change the global topology. So the diffusion is local, but the consequence is global. Okay, the connectivity of the global magnetic field is changed. Okay, and then after the reconnection, you see that these loops are actually ejected outward. Okay, partially by Lorentz force. Okay, so Lorentz force will work on the material and dissipate part of the energy. So on a global scale, it might not be the diffusion that is actually dissipating the energy. It's probably more of Lorentz force or some other forms of global processes. Okay. So for this course, we are more interested in the magnetic field configuration or the processes that's relevant to flares. So the most cited flare papers are probably this set of 4 papers authored by Carmichael, Sturrock, Hirayama, Kopp, and Newman. Okay, so I think it's Shibata-san in the 90s who took the first letter of all the authors and called it CSHKP model. Okay, so this is sort of the standard flare model. It's a combination of all the interesting features or the correct features in all these 4 papers. As you can see, each model has something interesting, and they are not. None of them is completely, complete or completely correct. I would say, all right. But they have some interesting features. But the interesting thing, and I have to confess, is that I haven't read any of these papers, but people cite them anyways, and they cite 4 papers together. So you will always see these 4 papers cited, but they were seldom read, I would say. It's kind of interesting. But I guess, from look at the cartoons, if you compare this cartoon with what I'm going to show next, okay, so this is sort of a more complete view of what goes on in 2D. They actually have almost all the important features, okay? So I'm using this Martins and Quinn cartoon in 1989 to talk about some of the interesting features. First is the pre-flare configuration, okay? So for the next rest of the class, I will mostly talk about this part, okay? This, in 2D, it's a circular shape. Magnetic field lines are sort of in circular, okay? So you could think of that in 3D. If you extend that, that is a flux rope, basically, okay? It's a flux tube, twisted flux tube. Or, to a less extent, it's a sheared, you have some component out of the plane of this screen, okay? So that's the part that's being ejected in this case, and that's, we could say, the CME. And in this particular configuration, there is a dark filament material, plasma, okay, that is supported by the magnetic field tension force. It just sort of hangs out there, supported by the tension force against gravity. And when this flux rope gets ejected, somehow this filament will get ejected. And that is the dark filament material you just saw in the AIA movie, okay? Then, okay, so in order for these magnetic structures to get disconnected from the pre-flare or the other loops, okay, closed loops, you will need to have magnetic reconnection here. So this is the current sheet we just talked about, okay? So during reconnection, you will need to have plasma inflow and you have plasma jet outflow, okay, at alpha speed. And then you will somehow accelerate particles here, okay, either through turbulence or some other mechanism, okay. So you will have higher energy particles going up and going down, okay. So if you have these high energy particles streaming down, in the corona, the density is low, okay. So these energy energetic particles will less likely collide with other particles. So they will sort of, go unopposed all the way until they reach this dense layer of chromosphere first, okay? Once it reaches there, it will collide with the plasma there and will transport part of its energy to the chromosphere material, okay? And the chromosphere material will be heated. And then they will just, if you think about water vapor, okay, it will just expand and fill the coronal loops, okay? And they will be ionized, of course. And so it will move along the loops. So all the bright loops, the post-flare loops you observe are the, in the lower energy, in UV or soft X-ray, are the cause, are the consequence from this high energy particles, okay? High energy particles comes down, energy gets thermalized and transfer energy to the chromosphere material, and it re-evaporates, okay, and fills the loops, okay. And of course, the foot points of these loops, okay, will be brightened because this chromosphere plasma just gets heated, okay. So this is the chromosphere flare ribbons you just saw, okay. And for the these non-thermal particles, high energy particles, it will also have a signature of a hard X-ray, okay. Usually what you see is a hard X-ray near the, sometimes you see hard X-ray signatures at the loop top, and most of the times you see it at these 2 foot points, right? What else? Yeah, on the right-hand side is actually a more zoomed in, okay, view of these post-flare loops. So that's what remains from this flare and CME process. The CME is gone, and you are left with this emitting plasma in the loops, okay. Okay, so let's see what else. Okay, that's actually all that I want to say for now. Okay. Oh, and also what I want to mention is that I talked about the flare, the magnetic field being non-potential, and there's electric currents. Okay. So once the CME is erupted, okay, part of the energy is taken away. Okay. So part of the free energy is taken away. For example, presumably what's left should have less free energy. Okay. And you would expect the loops to be less non-potential or more potential. And also because of the reconnection, your loop connectivity will no longer be the same. Okay, so the loops will be more potential. And the flare ribbon, okay, the flare ribbon you see at each time will map to the field lines that's newly reconnected at the current sheet. So that's a very important fact. At each moment, you see ribbons, and then you see these loops. So these newly brightened flare ribbons are the foot points of the newly reconnected loops. So by looking at the ribbon area, you can actually measure how much flux has reconnected, at least in this 2D approximation. All right. So that's some of the things that I want to talk about with this cartoon. The energy, okay, so I mentioned the Wattier's theorem. You are actually going to try to prove that, okay? It's not that difficult if you actually sit down and work it out. And the magnetic free energy, if you have a coronal model or have coronal field measurements, you can just calculate this, calculate it like that. But it's a very difficult problem, as I will show in the next lecture. So for flare, typical flares, now we have so much observations in different channels. People have done a tally of the energy content. Okay, so how much energy is there in magnetic fields? How much energy is transferred into hard X-ray, soft X-ray, for example? How much is transferred into electrons? Okay, how much is transferred into ions? How much is transferred to CMEs, how much is transferred to the energetic particles observed there at the Earth, okay? So this is a number that these authors gave for about 40 large flares. There are new estimates recently, okay? But the basic idea is that the CME will take a large chunk, and the electrons will take a large chunk. In the newer updated charts 2 years ago, the electrons is thought to have a larger chunk, okay, comparable more than CME. But this is still in debate. But in any case, okay, all this energy, if you add them all together, and if you are confident that you have counted everything, they should be the same as the magnetic energy, free magnetic energy dissipated in the flare, okay? And that is a portion, small portion of the total magnetic free energy. So that's the basic idea. And I talked about non-potentiality. So how do we actually look for non-potentiality? We talked about this complexity, and quantitatively, what does complexity mean? Okay. So what we are looking for usually are the signatures from photosphere to low corona near the polarity inversion line, or the so-called filament channel. Okay. We look for shear and twist if we can measure the energy in this free energy measurement. We look for electric currents. And if you can measure helicity somehow, helicity is also a measurement. So in this particular case, the authors developed a coronal field model, okay? So when you have a 3D model, you have a sense of the where the electric current is localized in 3D. So in this case, it's sort of in a very S-shaped or twisted structure in a very low corona, okay? This is also my personal preference. So this is a so-called momentum. We talked about energy, okay, and there's energy equation in MHD, so on. But there's also momentum equation that has not been discussed very much if you look through the literature, okay. So I was made aware of this problem by first paper by Hugh Hudson in 2012, where he proposed this concept and they estimated the breakdown of momentum of different processes, okay. For example, you have CME, okay, you have a CME mass estimate and the velocity estimate. Then you have this evaporation flow, okay, and you have waves, you have electrons, so on and so forth. All these momentum should be compared to the other force impulses, such as the Lorentz force impulse, the gravity force impulse, the pressure gradient impulse. Okay, so that is something we are looking into right now. The big difference here is that these values are signed. Okay, in energy measurements, everything's unsigned. You measure something, that's it. Okay. Here, when you measure for example, the evaporation flow, okay, you have a force acting on the evaporation. You have a counter force. Or if you have a jet, reconnection jets, you have upward jets and downward jets. These are signed, okay. So if you want to count the net value, you will have to take that asymmetry into consideration. So it's as I see it, it's a more complex problem. Okay, just like the last talk, I'm gonna end with several spectacular movies. This is a large flare from 2 years ago, about 1.5 years ago, 2017, September. That is one of the largest flare of this current cycle, okay. X8 on the limb. I call it the perfect storm because it resembles the 2D cartoon you just saw, every aspects of it, okay. If you look into the literature, there are about 50 papers published on this event already. All aspects you can think of in that cartoon have been explored with newer and better observations. So a few things, okay. So you can see here, when it first erupts, you can see a cavity like the ones teardropped, flux rope type of structure. Okay, that's a density deficient because you have stronger magnetic fields. You have a density deficiency, just as the flux emergence case, right? Then you have this very narrow sheet. It's probably not clear here, but it's a current sheet. Okay, that stretches out. Then you have these post-flare loops, okay, very cuspy, you have pointed structure. Then you have very, very bright post-flare loops, okay. And yeah, all these are more or less consistent with this 2D cartoons. This is one of the perfect storm, okay? So this is a more closer view, okay? So it's early on, you have these kind of loops surrounding this internal structure, which we interpret as a flux rope. So actually, it also flared about 4 days ago when it's on disk, where we do have the magnetic field observations, and we modeled, we did find flux ropes, okay? Just saying. Then with AI, you can estimate the temperature and density and so on. This one is a slightly different, it's a different event, but similar to this one. You see the CME going out, then in the wake of CME, you see this very linear structure, okay? And that's interpreted as a structure that surrounds the current sheet, okay? And if you look carefully, if you analyze the density or the brightness within this linear structure, you will see fluctuation and you will see blobs. And those have been interpreted as tearing mode instability that is thought to be a major mode of reconnection in the current sheet. All right, so these are the perfect examples of 2D. But okay, we know the sun is 3D, okay? So we know that it's not, you know, the flux rope is not a perfect cylinder, okay? So eventually we need to go to 3D. So what is actually different in 3D, okay? I'll talk about it in the next lecture, but here's just a brief taste. So for 3D, okay, this is active region, okay? It actually decays somewhat before it flares. So after it decayed to this kind of configuration, this is a very, very typical for, you know, CME and flares, active region CME flares. You have this S-shaped larger loops, okay? All right, this is a sigmoid, okay? You can see this in EUV and X-ray. And you have these filaments somewhere in between most of the time, okay? And some of the times, this sigmoid is not continuous. You see, instead of one sigmoid, as you see two J's. The J is broken in between sometimes, okay? This is not clear here. But obviously, you know, if there's a 2D cartoon, it should be symmetric all the way from top to bottom, right? But that's not the case. You have some asymmetry in this, this direction, okay? So that's one thing you have, because it's anchored in the photosphere and it's curved. So this is a geometry that cannot be modeled at 2D. Another effect that cannot model in 2D is just look at the flare ribbons, okay? So in 2D, you have this two ribbons that is symmetric with respect to the neutral line. But in reality, what happens is that the flare ribbons do not appear perpendicular, you know, asymmetric with respect to the neutral line. In fact, they appear to move along the ribbon, okay, first in this direction. And when it reaches the edge, it curved back, okay, it moves this way first. After a while, then it starts to expand more symmetric with respect to the neutral line in the two directions, towards the left and right. So this first stage that is, you know, moving along the ribbon, that aspect is complete 3D effect that cannot be modeled in 2D. And also, we'll talk about in the next lecture, this curved structure is a signature of flux rope. Okay, it's very telltale. And we talked about the reduction of non-potential energy, and we talked about non-potential energy being manifested in shear, okay? So, and we talked about the brightening of the flare ribbon is the newly reconnected flux, okay? So we can, basically we can count, you know, we can make this connection from this ribbon to this one, what the pre-flare loop is and what the post-flare loops look like. So pre-flare, the loops are sheared, okay? It's inclined with respect to it's more parallel with respect to the neutral line. But after the flare, if you look at the same foot points, the flares, the loops are more perpendicular to the neutral line. So that's a sign of reduction of non-potentiality. So that's also obvious in observation. All right. So with that, I think I'll stop here. And if you have any questions.
I had just, well, maybe not a question, but just to see if I understood this properly, because I don't know anything about these things. If it concerns the first part, so basically we get reconnection when the flux is emerging, and then it emerges in such a way that we get conveniently placed opposite polarities, and then these polarities reconnect, and then we see this small-scale reconnection in photosphere and chromosphere, right?
Yes, that's one way to make the flux emerge. Yes.
Okay. Okay. Good. And basically, interesting ways to observe that is using what you said, is using the telescopes which have good angular resolution, like Sunrise or Hinode or something like that.
Yeah. I mean, that's a signature of interplay between convection, surface convection, and flux emergence. And many of the flux emergence model does not have a convection, of course. So that particular, convection-driven reconnection will not, play a role. But reconnection there will still play a role, and it's very important. It's just that it's not driven by convection in those cases, but by some other factors.
Okay, thank you.
All right. Okay, I'll see you next week then.
See you next week.